Hello and welcome everyone with a very good morning to one and all. I guess everything fine, audible and visible. Let me know once is everything fine. Can somebody let me know? Good morning Binodini, good morning Pallavi, good morning everyone. Can somebody let me know is everything fine? If everything fine, then we will start in a minute. Varsha, good morning everyone. Let me first introduce that what actually we are going to do in this lecture series. Okay, you all were every time you all were asking that whether we can have a lecture series in English or not. Okay, so we are starting a lecture series in English. Okay, we will have this lecture series on group theory. We will have 6 lectures, and if you are interested, if the response is good, we will extend this lecture series to the next week also. Okay, so this lecture series will be in English, and we will discuss some basic things about group theory. If you are just starting with the group theory, it will be helpful for you. And if you have already prepared about group theory, then it will be helpful in the sense you can recall everything, okay, and it will revise everything whatever you have studied. Okay, so we will start this lecture series, and let me tell you what we are actually going to cover in this lecture series. We will have 6 lectures, and we will start with the basic definitions. First lecture will be on basic definitions. In this lecture today itself, we will discuss some basic definitions of group theory. Okay, good morning everyone, and thank you everyone. I guess सब कुछ ठीक है. Okay, so our first lecture will be on basic definitions. We will discuss some basic definitions like what is group, what are some properties of a group, and like what is order of an element, and some basic examples also of group. Okay, then we will move to the cyclic groups. In the next lecture, or in the second lecture, we will discuss about cyclic groups. Next lecture will be on permutation groups, and permutation group is important. I think it will need 2 to 3 lectures, but we will only take 1 lecture for permutation groups. We will discuss some basic things about permutation groups. Okay, and if it is needed, as I told you, we will extend in the next week. Okay, next lecture will be on external direct product. We will discuss basic properties and basic definitions and everything related to external direct product. And next lecture will be on normal subgroups, lecture number 5 on Friday. Okay, and in the lecture number 6, we will discuss quotient groups. Okay, so we will have 6 lectures on group theory and in English. Okay, good morning everyone once again. I guess everything perfect. Okay, if everything perfect, then we will start with the first lecture on basic definitions. Okay, so this is our lecture on basic definitions, and the first definition will be our definition of group. Okay, what is the definition of a group? See, to start study with the group theory, the prerequisites are like you should have a basic knowledge about set theory, like what are sets, what are some properties of sets, what are some basic operations like union and intersection operations. If you have some basic knowledge about sets, then you can start with the group theory. Okay, so let's first see the definition of group. What is definition of group? Okay, if we have, let's say, a non-empty set G with an operation star, I'm just saying that it is an operation star. Okay, if we have a non-empty set and we have an operation star, if with this operation star, this non-empty set G have 5 properties, or I would say 4 properties. If it has 4 properties, what are 4 properties? We will discuss that. If it has these 4 properties, then it will form a group. Okay, what are these 4 properties? The first property will be, if we consider any 2 elements of the group, let's say A and B, any 2 elements A and B, and we do the operation star with them, let's say A star B, it should again be inside G. A star B should be inside G for all A comma B belongs to G. Okay, we call this property as a closure property. Closure property. Okay, if you say star is a binary operation, or you say it is a closure property, or G satisfies closure property with operation star, they are same things. Okay, whether you say it's a binary operation or you say G satisfies closure property with this operation star, they are same thing. When you say it is a binary operation, what is binary operation? Binary operation is nothing but a map from G cross G to G. G cross G to G. When we say that it is a binary operation, it means that it is a map from G cross G to G. G cross G to G, it is a map means what? It means that whenever we take two elements from A to B, let's say phi of A comma B, any element from A comma B will, G cross G will be look like A comma B, okay? It should map to, let me say, A star B. Now you can say phi is a binary operation, or you can say star is a binary operation. Both are same things, right? A star B, this should again be inside G. For all A comma B, for all, let me say, A comma B belongs to G cross G, right? So whenever we have a star a binary operation, you can say star a binary operation, or it is sufficient to say that star satisfies closure property on group G, or G with operation star satisfies the closure property. This is our first property that we need to be a group, okay? The second property is associative property. Associative property is, if we, let's say we have three elements A comma B comma C, and we do operation of A and B first, A star B, then we do the operation with C, or we do operation of B and C first, B star C, and then do the operation with A. They will be same for all A comma B comma C belongs to G. This is called the associative property. Okay, it should be for all the elements of G, A star B star C, or A star with B star C. It should be same for all A comma B comma C belongs to G. As I told you, if we have, let's say, three elements, any three elements of the group G, and we do the operation of first two element, okay, Varsha, correct, we will see that, na? So if we have, let's say, any three element of the group G, first do the operation of first two element and then with the third element, or you do the operation with the last two element first and then do the operation with the first one. There is no difference, okay? It is called the associative property. Let's move to the next property, and it is called existence of identity. Okay, what does it mean by existence of identity? We should have, let me write it, this is called associative property. Associative property. Okay, we will discuss some examples, then you will get it, it will be more clear to you, okay? So the third property is, it is called existence of identity. What does it mean? It means that we will have an element inside G, and it has the property that whenever you do the operation with that element, you will get again the same element, original element, right? What does it mean? It means that there exists an element E belongs to G such that E star A or A star E, this is equals to A for all A belongs to G. This is called existence of identity, and the element E is called identity element. Existence of identity, and this element E is called the identity element. This is always unique in a group, okay? Whenever we have a group G, it is a unique element in a group G. We cannot have two identity elements, or you can say we cannot have two elements E1 and E2 which can have this property. Whenever they multiply with any element, they should give again the original element, okay? This is called existence of identity. We should have an identity element, okay, which has this property. And the next property is existence of inverse. What does it mean by existence of inverse? If, let's say, if we have A belongs to G, okay, for, let me write in this way, for all A belongs to G, there exists B belongs to G such that A star B, B star A is equals to E, okay? For any element A of the group G, we should have an element B inside G itself, okay, such that their operation becomes identity element. For any element A, we should have a B, such that their operation becomes identity element. These are the four properties. If some non-empty set together with some binary operation star, we have these four properties, we say that it is a group, okay? For example, let's say, good morning, what is her name? Ilumalai. Okay, so the first example and the first example of the group you can consider is, let's say, Z with the operation star. Z with the operation star. It has all the properties whatever we have discussed so far, okay? The first property was closure property. What does it mean by closure property? Whenever we take two elements, the operation should be again inside the group of the set whatever we are considering, right? And it will have if you consider, let's say a comma b, any element a comma b belongs to z, let's say, and if you add them, the operation is addition. Okay, when we add them a plus b, if you add two integers, again we will get some integer, right? So it will be inside z. A plus b belongs to z for all a comma b belongs to z. We all know this, right? Whenever we add two integers, we will again get some another integer, correct? So it has binary operation. You can say addition is a binary operation, or you can say G with the operation star has closure property. Okay, both the things are correct and they're equivalent. There is nothing difference. Okay, next property is associative property, and integers have associative property also with respect to operation addition. It means that if we have, let's say a, b, c belongs to z, if we add a and b first, then we add c, or we add b and c first, then we add a, there is no difference in the integers. So in whatever ordering you are adding the elements, there is no difference, right? For all a comma b comma c belongs to z, for all a comma b comma c belongs to z, correct? So it has associative property. Next is existence of inverse. Can you guess what can be the identity element of z with respect to operation addition? What can be an element so that we can add with any other element, it should again give the original element with respect to addition? I already told you add, right? So what is the element inside z? If we add to any other element, we should give again the original element. Let's say we have a, what we can add with this so that we can get again a. 0 is the element, right? If we add 0 to any integer, we will again get a. A plus 0 is a for all a belongs to, for all a belongs to z, right? And 0 belongs to z. So z has additive identity, you can say. Z has identity element with respect to operation addition. So the third property, existence of identity, is also satisfied. It means that z with operation addition has identity element. Is that clear? Next is existence of inverse. Let's say, what does it mean by existence of inverse? If we consider any integer, let's say a belongs to z, okay, we are looking for an element, let's say b belongs to z, such that a plus b, if we add them, it should give identity element. What is identity? 0. It should give 0. What can be the correct example, right? 0 was the additive identity. And what about inverse? If I consider any integer a, what can be the inverse of that integer? Minus of that, right? If we, let's say, have a belongs to z, then you can say then minus a belongs to z, minus a belongs to z, such that a plus minus of a, it is equals to 0. Correct or not, right? And if a is an integer, minus of a will also be an integer, right? So there exists inverse element for every element, correct? Okay, so it has existence of inverse property also, correct? Minus of a is the inverse of any element a belongs to z. So it has existence of inverse property also. That's why it has all the four properties. So z with operation of addition, therefore z with operation addition is a group, correct? So this is the first example of a group. Okay, what is abelian group? If somebody you know, you can answer this also. What is abelian group? This abelian group, as from the name itself it is clear that a group has some extra property, right? It is already a group, right? So if we have, let's say, G with the operation star, if let's say G with the operation star be a group, let me write, let G with the operation star be a group, okay, we say that G is an abelian group. G with the operation star is an abelian group if it has one extra property, is the commutativity abelian group. Okay, we say that G is an abelian group with the operation star if, let's say, we have commutativity, if G have commutative property with respect to operation addition, or you can also say that A star B is equals to B star A for all A comma B belongs to G. What does it mean? It means that if we do the operation of A with A, B, or we do the operation of B with A, it should be same. Okay, there is no difference by changing the order of elements. Is that okay? So if we have a group and it has one extra property, the commutative property, we say that it is a abelian group, right? The example can be Z with the operation addition itself, right? To be an abelian group, we should have 5 properties, right? All the 4 properties are already needed for it to be a group, right? And the extra properties for an abelian group, correct? The example can be the same example we have considered. Z with operation addition is an abelian group, Do you agree or not, right? It is an abelian group because it has the property, it has the commutative property. This property is called the commutative property. We sometimes we call it as a commutative group also, okay, because of the name of property, commutative group. Commutative property, we call this property as commutative property. Together with the 4 properties, if G with operation star has this property also, then we say that it is a abelian group. Like Z with operation addition is a abelian group. Why this is a abelian group? If we consider, let's say A plus B, this is same as B plus A for all A comma B belongs to Z. Correct or not, right? If you add 2 integers in any order, right, whether you add A to B or B to A, there is no difference. We all know this, right? So that's why this is a abelian group. Okay, I think it is clear up to here. If there is any issue, if you didn't get anything, you can ask me immediately. I will respond. Okay, now let me ask you some basic questions. Let me check it that whether you are getting or not. Okay, the first question is, can you answer this if you get all the things? And let me introduce a few more terms and then I will ask questions. Okay, let's say if a non-empty set G with operation addition only have this property, let's say this property, closure property. If a non-empty set together with a star operation has only one property, the closure property, then there is a special name for that structure G with operation star. It has a special name, it is called groupoid. Okay, let me write it here. What is groupoid? You should know these terms. The definition of a groupoid is simple. A non-empty set. If you want, you can write. I think it's easy to understand. G with the operation star is groupoid, or let me say G is a non-empty set. A non-empty set G, or let me explain it here itself, right? They're not too much important. You should only know about that. Okay, so let me write it here itself. So whenever G with the operation star, a non-empty set G with the operation star has only closure property, okay, the first property, or you can say a non-empty set with a binary operation star, it's said to be a groupoid. It's a simple definition. Okay, correct. Then if let's say a non-empty set together with a binary operation star has 2 properties, the closure property and the associative property, there is a special name for this structure and it is called a semi-group. Got it? So semi-group. Okay, please do remember it because I am going to ask some questions on these definitions. Okay, so what is a semi-group? A non-empty set together with the binary operation star, if it has 2 properties, the first is closure and the second one is the associative property, we say that it is a semi-group. Okay, if let's say it has 3 properties, non-empty set together with the 3 properties, and one is closure, another one is associative, and the next one is existence of identity. We have a name for this also. It is called monoid. We call it as monoid. If it has identity element also with respect to operation addition, okay, we call it as a monoid. Okay, if it has all the property, then we already know, we say that it is a group. Okay, and if it has the 5th property also, we say that it is an abelian group. Okay, we got all the terms. I think you will understand, and if you didn't get, please ask me. Okay, let me ask you some questions now. If you understand all these definitions, let me remind you once again. Groupoid, what is groupoid? Non-empty set with the binary operation star, or you can say non-empty set with the operation star, and if it has closure property, we say that it is groupoid. If it has these 2 properties, closure and associative property, we say that it is a semi-group. It has 3 properties together with the first 2. If it has identity element also, we say that it is a monoid. These are the some definitions. Let me ask you now some questions. Okay, what do you think about this? If I ask you, let's say the question is, n with the operation star, the set of natural numbers with the operation star is, the operation first is groupoid. What do you think? Is it a groupoid? Is it a groupoid? And the option B is it a semi-group? Is it a semi-group? Option C is it a monoid? Is it a monoid? And option D is it a group? What do you think? Let me see what will you answer. The set of natural numbers with the operation addition. Is it a groupoid? For groupoid, we need only closure property. Is it a semi-group? Is it satisfied? Or you can say the set of natural number has associative property with the operation addition also. And the next is monoid. Is it monoid also? It means that it have identity element also with respect to operation addition, and is it a group also? It has all the properties. What do you see? Rashmita, you see it is a semi-group. It means that if it is a semi-group, okay, Shakshi, Rampal, okay, you all agree that it is a semi-group. It means that it is a groupoid also. So option A is also correct. If it is a groupoid, so we can have these observations, right? You can say every semi-group is a groupoid. Agree or not? Every semi-group is a groupoid. Every monoid is a semi-group, so that it is a groupoid also, and every group is a monoid also, and so that it is a semi-group and groupoid also. So you should have these observations. So which is correct? B is correct, and so A is correct. Since it is a group semi-group, and to be a semi-group, it should first be a groupoid, right? You can say that a groupoid is said to be a semi-group if it has associative property. Agree or not? So A and B are correct. Why A and B are correct? The first property to be a groupoid is it should have a closure property, and B, we know that if we add two natural numbers, A plus B belongs to N for all A comma B belongs to N. Whenever we add two natural numbers, we will again get a natural number, so not an issue to be a groupoid. Okay, correct. Is it a semi-group? Yes, it is a semi-group also. If we have in any order, let's say we add B and C first, then we add A, or we add A and B first, then we add C. For all A comma B comma C belongs to N, there is no difference between them, right? So it has associative property, and so it is a semi-group also. Next is monoid. Is it a monoid? No, it is not a monoid, because with respect to operation, the identity element can be zero element, but N does not have zero element. Agree or not, right? Because N does not have zero element. We know that A plus 0 is equals to A for all A belongs to N. But the problem with this is, but 0 is not inside N. Correct or not, right? So which implies that this is not a monoid, and since it is not a monoid, how it can be a group? It is not a group. Correct? Let me ask some more questions. The next is, just a second. Okay, Z with operation addition we have already discussed. I think, let me ask you, let me see what will you answer. Z with operation addition is, let me see, option A is groupoid, option B is correct. See now, option B is let's say semi-group, same options. Option C is monoid. Let me see what will be answer for this question, and then I will ask some more. Option D is group. What are options are correct? Z be the operation is, which of the following is are correct? As I told you in the last question, that maybe more than one options can be correct, so be careful. What do you think? All correct is us. Rampal correct. Shakshi correct, and Rashmita correct. A, B, C, D is also correct. Rashmita, Varsha correct. Right? So all the options are correct. A, B, C, and D, all these options are correct. It is a groupoid, it is a semi-group, it is a monoid also, and it is a group. Because we have seen that the first example we have discussed was Z with operation addition. We have seen that it is a group, and if it is a group, then it is everything. Whatever we have definitions so far, right? So all are correct. Next, let me ask you this question. Every semi-group is, let me ask you in this way, every semi-group is, the first is groupoid, option B is, let's say, monoid, option C is group, and option D is none of these. What do you think is the correct option? Correct. Every semi group is A. A and B. No, is that only option A is correct. Why B is correct? We have seen NB the operation addition by the semi group, but it was not a monoid, right? Only A is correct. Is that clear? Correct. A is correct. So whoever is answering A is the correct option. It is a monoid because to be a semi group, we should have two properties. One is associativity, another one is closure property. It has closure property, so it is groupoid, but it may not have existence of identity property. Like we have example Z with the operation addition. It was a semi group. It was a semi group because it has closure property and it has associative property, but because it does not have identity element, so how it can be a monoid, right? It is not a monoid, and since it is not a monoid, so it cannot be a group also, and none of these will also be discarded. Only option A is the correct option. Let me ask you some more questions. If I ask you Z be the operation subtraction, Z be the operation subtraction is, which of the following is correct? The first is, let's say, group wide again. Option B is semi group. Option C is monoid, and option D is group. See, I know that these terms are not very much important, but still if you know all these terms, it will be like you will have some mastery in defining a group, or you can say verifying a group, whether a given non-empty set with the operation star is a group or not. Okay, if you know all these things properly, then you can easily verify that whether a non-empty set is group or not. Sapna, good morning, and good morning everyone once again. Example A versus C, okay, or Sakshi A, correct, okay, let's see. It is a groupoid, and what about others? Is it a semi group? Is it a monoid or not? It is only a groupoid. A is the correct option. That's what we miss. No? It does not have associative property. Okay, so it cannot be a semi group, and if it is a not semi group, then there is no need to discuss the next terms, right? Like monoid and group or abelian group. No? When it is not a group, then why we will discuss other things. It is only a groupoid. Z with operation addition is only a groupoid. China, Sapna, Izaz, Dhanashri, and everyone correct. A is correct. Rashmita correct. It is only a groupoid. Why it is a groupoid? Sushma correct. So if we consider, see, we already know if we consider any two elements and do the subtraction, we will again get another integer, right? There is no problem with that. A minus B belongs to Z. For all A comma B belongs to Z. Closure property it has. This is the closure property, so it is a groupoid. Okay. Next is semi group. It is not a semi group because the associative property it does not have. If we consider, let's say 1, 2, 3, if it has associative property, it means that it should be for all the elements, right? Let's consider 1, 2, 3 belongs to Z. These are the integers. If I find, let's say 1 minus 2 minus 3, and it is not same as 1 minus 2 minus 3. If we do the operation of 1 and 2 first, then operation with 3, or if we do the operation of 2 and 3 first, then with the operation 1, they will be different. You see, what is this? This is 1 and plus 1, it will be 2. And what is this? This is minus 1 and minus 3. It is minus 4. They are different. So it does not have associative property. It means that it is not a semi group. So it cannot be monoid, and so it cannot be a group. Correct? So option A is the only correct option for this question. Let me ask you some more. Okay, what do you think about this? Let me consider Q with the operation addition. Q means set of rational numbers with the operation addition is, the first is groupoid. Option B is, let me say, semi group, and option C is monoid. Option D is again group. What do you think? And let me give you option E also. Is it abelian group? Because we have already discussed the definition. We have seen the definition, abelian group. So what do you think are the correct options for this question? Can you answer this? Q with the operation star, is it a group wide? And please do check all the properties. When we say that it is group wide, it means that we need to check the closure property. When we say that it is semi group, it means that we need to check for associativity also, right? And when we say that it is monoid, it means that we need to check for identity element also, correct? So do check all the properties and then let me know. Sapna, when we say D means A, B, C, D, all are correct. A, B, C, D, E, all are correct. Correct? Illuminai, what is your name? I don't know. Tanashri, correct? Correct. A, B, C, D, E, all are correct for this question. Okay. It is group wide whenever we take, let's say, two rational numbers. Let me write in this way: P1 upon Q1 plus P2 upon Q2. Okay, any two rational numbers, the addition will always be a rational number belongs to Q for all P1 upon Q1 comma P2 upon Q2 belongs to Q. So it has a closure property. Next is semi-group. Associativity also there with respect to addition. There is no problem in any group, any non-empty set, right? Addition is associative. This is the property of a operation, right? It is a semi-group also. I think you all know. If there is any issue, you can comment and I will explain this in detail, okay? Next is monoid. It has 0 element. 0 belongs to Q. If we add 0 to any element, P by Q plus 0 is equals to P by Q for all P by Q belongs to Q. Right? If we add 0 to any element or any element to 0, we will again get the same rational number. Okay, so it is a group also. Since it has, okay, we didn't discuss about inverse property, and we have inverse also. Whenever we consider, let's say, P by Q belongs to Q, we will have minus of P by Q belongs to Q. This minus P by Q will be the inverse of P by Q. If we add them, we will get 0 element, which is identity element, correct or not, right? And if P by Q is a rational number, minus of P by Q will also be a rational number. So we are not going outside to look for the inverse, right? So it has property. Abelian group, because we know that if we add in any order, okay, you add P1 by Q1 to P2 by Q2 or P2 by Q2 to P1 by Q1. There is no issue with that, right? They are same. For all this P1 by Q1, P2 by Q2 belongs to Q. So this property is also satisfied. It is an abelian group. Now we have another example. Z with operation addition was an example of a group. We have one more example. Q with operation addition is also a group. In the same way, you can consider this is also a group set of real numbers with operation addition. This is a group. You can check that. And moreover, it is an abelian group. This is an abelian group. Okay. C with the operation addition, this is also a abelian group. You can check for it, okay? They all are abelian groups. Next question, let me ask you. The question is, which of the following is our groups? Which of the following is our groups? Now we are in flow. We have already checked monoid and everything. Now we can check for group. Which of the following is our groups? Is our groups, okay? Some simple examples. Let's say the first option is M n cross n R with operation multiplication. Let me introduce what is this with operation multiplication. Multiplication you all know, and when we said multiplication, it is matrix multiplication. Matrix multiplication. Multiplication. What is M n cross n R? M n cross n R is the collection of, or let's say set of, all n cross n matrices. All n cross n matrices with real entries, okay, this is our set M n cross n R. Option B is ZL2 comma R, okay, with operation multiplication. And what is this? This is collection of all non-singular matrices. Let me write it in this way. ZL2R. What is ZL2R? ZL2R is, let me define in this way. It is defined as A belongs to M2R, M2 cross 2R, or simply you can write M2R, M2 cross 2R, such that determinant of A is not equals to 0. The collection of all non-singular matrices. Okay, what do you think about this? And option C is SL2 comma R, SL2 comma R with the same operation multiplication, matrix multiplication. Is it a group or not? How SL2R is defined? We are considering all the elements A belongs to, let me say, ZL2R, whose determinant is, यहाँ पे मैंने क्या लिया? We have considered determinant should be non-zero, but now we will consider determinant should be non-zero, and more than that, it should be equals to 1. determinant of A equals to 1. So collection of all 2 cross 2 matrices whose entries are coming from real numbers and they have determinant 1. Correct? So this is our SL2R. The next is none of these. So what do you think are the correct options? None of these. Which of the following is R groups? What do you think about that? A not a group, inverse of non-singular matrix. Very good, Dhanush. Correct. A is correct. It is not a group. I know what others are thinking. Let me know. Which of the following is our groups? Shakshi, B, C, Rampal, B, C, correct. B is a group and C is a group. Okay, correct. Danishri, okay. B, C. Illuminati, A is not correct. Okay. Is as B, C, Rashmita, Rekha, Shabna. B and C are the correct option. Now we have some more examples for the groups, right? Just like B and C, they are groups, right? B and C. Let me explain this. See, when we consider this one, collection of all 2 cross 2 matrices whose entries are coming from real numbers. If we talk about the closure property, they will have closure property. Whenever you take, let's say, this is in general n cross n matrices. If you want to be precise, you can consider, let's say, 2 cross 2 matrices. You consider any 2 cross 2 matrix A, and let's say another matrix 2 cross 2 matrix B, and let me generalize it because I think you all know this, right? We from 10th standard we start studying matrices, so I think you all know this, right? So n cross n matrices, we take 2 n cross n matrices. If you multiply them, again you will get, let's say, C n cross n matrix, right? And if the entries of A and B are coming from R, the entries of C will also become from R, right? They will not be outside R. What we are doing when we multiplying, the addition and multiplication, right? If you add 2 real numbers, you multiply 2 real numbers, again we will get a real number, so it will be a member of M and R. So it has closure property. You can say M and N cross N or M and R, they are same. Okay? So they have closure property. It means that it is group-wide. Next property is semi-group also. The matrix multiplication is, or in general, the multiplication is actually associative. If you take 2 matrices, 3 matrices, let's say A multiplication B multiplication C is same as A multiplication B multiplication C for all A comma B comma C belongs to M and R. Okay, agree? It has associative property. Next is existence of identity element. It has identity element also, and the identity element is this. So it is a monoid as well. If we have asked you questions like we have asked previous some questions, right? So you can answer this. It is a monoid as well. Why this is a monoid? Because we have this matrix, let's say 1 on the diagonal and all other entries are 0. If you multiply this matrix with any other matrix, all the entries are coming from R also, so it is a member of M and R. And if you multiply with any other element, we will again get the same member whatever you multiply with. Correct or not, right? So it is a monoid as well, but the problem is with the inverse. If I consider, let's say, simple 2 cross 2 matrix, if I consider, let's say, this matrix, this is also a member of M and R. This is also a member of M and R, right? Or M2R, let me say. Correct? But it does not have multiplication in multiplicative inverse. There is no matrix such that we multiply with this matrix A into 0, 0. This will give you this matrix 1, 0, 0, 1. There is no matrix, right? So it does not have inverse. Not only this, any matrix whose determinant is equals to 0 will not have inverse with this identity element. Correct? With respect to matrix multiplication. So the problem with this is it is not a group because it does not have inverse property. If we introduce inverse property, if we consider, let's say, those element which has multiplicative inverse, then it may form a group, and that's what we do. That's what we did to construct GL2R. R, ZL and R also, you can generalize this. ZL and R. Okay. What we do? We have considered all the matrices from M and R which has multiplicative inverse, and which matrix has multiplicative inverse whose determinant is not equals to 0. We have considered all the matrices from M and R whose determinant is not equals to 0. Already we have all the property up to monoid, we have everything, right? The inverse property was not there, but we have considered all the matrices which has inverse, so it becomes a group. There is nothing to be proved. It is a group. correct? And this is a group and this is also a group. It has all the properties, closure property and everything it will have. Only you can check for inverse, right? See, associative property it will have, closure property. If you multiply two matrices whose determinant is 1, the product will also have determinant 1. You can easily check. I think you should check. Okay, if you are just starting, you have to check all these properties. Okay, whenever you consider, let's say, let me write it here, you consider A comma B belongs to SL to R, right? It means the determinant of A is equals to 1, determinant of B is equals to 1. Their entries are real numbers. They are 2 cross 2 matrices. If you multiply them, A multiplication B, you will get some C, and it will also be a 2 cross 2 matrices. Entries will be real, and the determinant also, if you find the determinant of A multiplication B, we know the property of determinant. This is nothing but determinant of A, determinant of B, both are 1, so it is also 1. It has closure property, right? The same way associative property, already associative property actually it inherits, right? Because it was already in MNR, it was satisfied by all the elements of MNR. It will be satisfied by the elements of whose determinant is 1, because it was already satisfied by all the elements, right? So it will be satisfied. It is an inheritance property. Okay, whenever you consider a subset also, it will have property in the subset also. Okay, correct. Then we have let's say existence of identity. The identity element will also be inside SL2R. Do you agree or not? Because the determinant of identity matrix is also 1, so it will be inside SL2R. We have existence of identity. Then existence of inverse. When we consider, let's say A belongs to SL2R, right? And let's say B is the inverse, or let me say A inverse simply. This is the inverse. It will have inverse, that we already know, right? Because the determinant is not equals to 0. But is it a member of SL2 or not? That we need to check. Correct or not, right? So the determinant of A inverse is nothing but 1 upon determinant of A. And this is again equals to 1 because the determinant is equals to 1. So it means that A inverse is also a member of SL2 comma R. We can write in this way also, or we can also write SL2R. So they are groups. This is a group. Okay, this is also a group, and you can generalize them also. Let me write here 2 itself, but you can write these as a point. Okay, S, L, N, and we can even consider any field, not only R. We can consider any field F. This is again a group. This is a group with the operation matrix multiplication. Is that okay? This is a group. We can consider G, L, N comma F for any field. If you can consider finite field, you can consider R, you can consider Q, you can consider C, it will always be a group. So it is always a group. They are groups. We have some more examples. All right, these are groups. Let me ask you some more questions. Okay, what about this one? The next question is, let A be any non-empty set. Let A be any non-empty set. Okay, then what do you think about the power set of A with the union operation is? What do you think about this? Is it a, option A is not a semi-group? Is it not a semi-group? Next is it a monoid? Is it a monoid? Option C is it a group also? Is it a group? And option D is none of these. What do you think? Just let me know. Think about this carefully and then let me know which option is the correct option. B, okay. Izas, Rekha, Sakshi, everyone. B, you all agree that B is correct? B means it is a monoid, okay? Sushma, Dhanashri, Sakshi, okay. B is correct. It means that it is a monoid. When you say it is a monoid, it means that it is a semi-group also. It is a groupoid also. Let's check it. Okay, let's check that. So first, to be a monoid, it should have closure property, it should have associative property, it should have existence of identity. All these three properties are needed. Then we will check for group also. Okay, first let's see whether it satisfies the closure property or not. What is power set of A? Power set of A is the collection of all subsets of A. Is that okay? So let's consider M belongs to power set of A. M comma N. Let me consider M comma N belongs to power set of A. When we say that M comma N belongs to power set of A, what does it mean? It means that they are the subsets. Okay. B and C. Okay. Many of you are agreeing that it is a group as well. Okay. We will see that. So it means that M is a subset of A and N is also a subset of A. Correct or not? Right? When we say that it is an element of power set of A, it means that it is a subset of A. Let's consider the union of these two, M union N. They are arbitrary elements, right? M union N. What do you think? If A is a subset, M is a subset of A, N is a subset of A, M union N will also be a subset of A. Agree or not, right? So M union N, this will also be a subset of A. Correct or not, right? It will not go outside because they are already subset. M is a subset, N is a subset of A. Then M union N. You all know what are union, right? Collection of all the element, whether it is an element of M or it is an element of N, right? So this is a subset of A. It means that M union N belongs to power set of A. Agree? Okay, fine. Next is semi-group. Does it have associative property? Union operation? Yes, it will have associative property. What is the problem with that? Let me consider, let's say M1 union M2, or you do the, let's say you do union with M3, or we do M2 union M3 first, and then we do take the union with M1. There is no difference. They will be same, right? If you take any union in any order, they will be same. There is no issue, right? So for all M1 comma M2 comma M3 belongs to power set of A. Agree? It has associative property. Next property is monoid. Does it have an identity element? When we say that identity element, it means that we are looking for an element, let's say E. E belongs to power set of A, such that if we take union E union M, this should be M for all M belongs to power set of A. So what can be the identity element? Phi. If we take union with phi, it will again give the same original subset whatever we have considered, right? So phi union M and also M union phi. This is equals to M for all M belongs to power set of A. It means that, and this is a member of power set of phi belongs to power set of A. That's why it is a monoid. It has identity element. Correct or not, right? So it is a monoid. Option B is the correct option. Let's look for group. When we say that it is a group, it means that monoid has one extra property, and the property is existence of inverse. Does it has inverse? Let's say M belongs to power set of N. If I consider, let's say M belongs to power set of A, and we are considering, let's say it is not equals to phi, because if you consider phi, and we know that the inverse of identity is identity, you can easily check that, right? If you do the operation of identity with identity, we will get identity. So there is nothing special for looking an identity element of so inverse element of identity, right? That is it's kind of useless, right? So what we do is we will look for the inverse element of some non-identity element except phi. Let's consider M is a non-identity element. It is not equals to phi. Then we are looking for an element, let's say, of the power set of A. We are looking some subset of A such that M union with that subset, it should give phi, which is our identity element. It should give identity element, which is phi. So what do you think? Does it have power set of A, or let me say, is there exist any subset of A such that M union that subset becomes phi? It will never be, right? We all know this, huh? Because M already has some element, and whatever subset here if you consider, since M is not phi, how the union can be phi? You cannot make it phi. Correct or not, right? So it does not have inverse property. Whenever you consider a non-empty set, it does not have inverse elements, so it is not a group. It is not a group. This is already discarded because it is not a semi-group, so not a semi-group is correct, not correct. None of these is also discarded. Only option B is the correct option. If there is any confusion, you didn't get anything, you can ask me. Is that clear to everyone? It is not a group. It will go up to monoid. Do you agree? Okay, let me ask you one more question and then we will stop here for the day. By the way, we have to discuss many things, many terms like what is subgroup and what is order of element. We will discuss in the next lecture. The next lecture is devoted to cyclic group, but anyway, in the starting we will discuss some more definitions. Okay, then we will start with the cyclic groups. I hope it is clear to everyone. Let me ask you one more question. And the question is, which of the following is wrong? Which of the following is not correct? We will start with this question. Okay, if let me see what will you answer. Which of the following is not correct? Which of the following, and let me say is are not correct. Maybe more than one option may not be correct. Is are, which of the following is are not correct? First option is the set Z of integers, the set Z of integers forms a group with respect to usual addition of integers. I think let me write it in a short form. Z with the operation addition is a group. Option B is this set 1 comma minus 1, okay, with the operation multiplication is a group. And C option is, let's say C star with the operation multiplication. Let me consider with the operation multiplication. What is C star? C star is defined as C minus 0, okay, all the non-zero complex numbers. And option D is Q with the operation multiplication. Set of rational numbers with operation multiplication is a group. This is a group. This is a group and this is a group. What do you think is are not correct among these four? Z with operation addition is a group. I think we have already discussed this. There is nothing to be checked. We have already seen this. So let me discard this because it is already correct, you know? Because we have checked that Z with operation addition is a group. Let me discard this. Now you check for others. Which of the following is are not correct? What do you think? B, okay. 1 minus 1 with multiplication is a group. You think this is not correct. Shakshi, you think D, okay. What about others? Izaz B, Rekha D, okay. Shapna D, okay, fine. China D, okay. Rashmita D, okay. What others? Shushma D, okay. So actually D is the correct option. This Q with operation multiplication is not a group. It's very easy to see that. It's very easy exercise to check that. Since 0 is there inside Q and 0 can never have multiplicative inverse because the multiplicative identity is 1. Correct or not, right? 1 is the multiplicative identity, is the identity of Q with the operation multiplication. Agree? Right? When if you are looking for, let's say, inverse element of 0, we are looking for some element, let's say Q belongs to Q such that 0 into Q becomes 1. Do you think so it will exist? 0 into any rational number, it will give you 0, right? There is no such number, hai na? So 0 does not have multiplicative inverse and 0 is inside Q. Every element should have multiplicative inverse, right? 0 does not have multiplicative inverse, so it cannot be a group. And it cannot be a group, it means that this is not correct. So D is the correct option for this question, okay. Next, let's say B, some of you thinking that B is a group and B is a group. This is correct actually. You are thinking that it is not a group. When you say that it is not correct, it means that it is not a group, you know? Correct. So it is a group. Multiplication with respect to multiplication operation, it is a group. It has every property. If you multiply them, let's say 1 with minus 1 for multiplication, or if it is a finite group, it has some, let's say 4, 5, 6 element, you can form Cayley table also. We call it as a Cayley table. Let's say multiplication operation, we have 2 element 1 minus 1, 1 minus 1, 1 multiplication is 1, 1 minus 1 is minus 1, minus 1 minus 1 is 1, minus 1 minus 1 is 1. So these all the elements are 1 and minus 1, they are coming from this set, right? So it has closure property. Next is associative. Associative is already there with respect to multiplication, not an issue, right? Set of real numbers in general, set of complex number has, and they are the subset of complex number, so it has. I told you, right? The associative property is the inheritance property, right? It inherits in every subset of the set. If set has associative property, then every subset of that set will also have associative property. Is that okay? So it has associative property. It has identity element also. One is the identity element. One you multiply with any element. We have only two elements. You can check that. 1 with 1 is 1. 1 with minus 1 is minus 1. So 1 is the identity element, and inverse also. The inverse of 1 is 1. 1 into 1 becomes 1. And inverse of minus 1 is minus 1. Minus 1 into minus 1 is equals to 1. Correct or not, right? And so this is our identity element. Is inverse also. Every property is there. So it is a group, and more than that, it is a abelian group also. Since it is a group, so it will be discarded. It is correct, but we need to choose the incorrect one. So it is discarded. Next is C star with operation multiplication. This is also a group. When we say that C star with operation multiplication is group, it should be clear that it will have closure property. Let's say Z1 multiplication Z2. This will also be, if they are two non-zero complex numbers, then it will be a non-zero complex number. For all Z1 comma Z2, Z1 comma, let me not Z1 in this way, Z1 comma Z2 belongs to C star. Correct or not? It will have associative property with respect to multiplication, not an issue at all. If you consider, let's say Z1 multiplication Z2 multiplication Z3, this will be same as Z1 multiplication Z2 multiplication Z3 for all Z1 comma Z2 comma Z3 belongs to C star, not an issue. And next property is existence of identity. 1 is there, non-zero complex number, 1 belongs to C star. If you multiply Z with 1, and we will get again Z, and this is same as 1 multiplication Z also. For all Z belongs to C star. It belongs to C star. It has C star, right? It has existence of identity property also, or you can say it has multiplicative inverse. Next is multiplicative inverse. When we consider, let's say Z equals to, let me say, x plus I by, this belongs to C star. What is the multiplicative inverse of this? The multiplicative inverse of Z is nothing but, Z inverse is nothing but 1 upon, let's say, Z, 1 upon Z, which is equals to 1 upon x plus I by. Maybe you are thinking that it is not a complex number. A complex number is of the form x plus I by, or let me say a plus IB, where a comma b belongs to Z, a comma b belongs to R, right? But if you rationalize it, we will get x minus I by upon x minus I by, we will get x minus I by upon x square plus y square. Now you see, x upon x square plus y square, this is some real number, plus, let me say, I times minus y upon x square plus y square. This is also some real number. So it is a non-zero complex number. This belongs to C star. This is a non-zero complex number because they are non-zero complex. Z is a non-zero complex number. X and y, one of them should be non-zero and one of them is non-zero. Then we will get, these are, one of them should be non-zero. If one of them is non-zero, then it is a non-zero complex number. It means that every element has multiplicative inverse also. See, we have all the properties, and it means that this is also a group, so it will be discarded. Only option D was the correct option for this question. I hope that everything is clear up to here. If any issue, you can comment, and comment here also. You can comment it later also. Okay, we will stop here for the day. In the next lecture, we will discuss some more definitions, like what is subgroup, how we can check for a subgroup, what are some more examples of a group, what can be the order of an element, how we can find the order of an element, and what is cyclic groups. Okay, we will stop here. Thank you everyone for joining, and see you in the next lecture on the same time. Okay, thank you everyone once again, and take care.